In this lecture, we will compare solid shaft with hollow shaft. First, there will be compression. We will compare by strength, compression in strength of solid shaft and hollow shaft for given condition, right? For this condition, when we are comparing the strength of these two shafts, right? So this is our hollow shaft. And this is solid shaft. Diameter of solid shaft is ds. Inner diameter of hollow shaft is dh, and outer diameter is capital dh. Now assume that length of hollow shaft and solid shaft is same. They are made of same material. Right? Weight of both shaft is same. And they have same maximum shearing stress, that is tau max hollow equal to tau max, solid equal to tau max. Right? These are the conditions given. Then we will go for the compression in strength. Clear? Assuming length is same, they are made of same material. That means density will be constant, and weight is same, and maximum shear stress developed on the periphery is same. Right? For this condition, we will compare the torsional strength of the shaft. Right? Now, say the torsional strength of hollow shaft is th, and it will be equal to pi by 16 into tau max d h to the power 4 into n to the power 4 minus 1 upon this will be dh cube, right? Dh cube n to the power 4 minus 1 upon n, right? Where n equal to capital dh upon small dh, that is n denoting the ratio of outer dia to the inner dia, right? And T solid will be pi by 16 into tau max into ds cube. If we are comparing it, then divide these two equations. Right? These both will be cancelled out. Tau max will be cancelled out. Finally, expression left is th upon ts equal to t h cube upon t s cube into n to the power 4 minus 1 upon n. Here n equal to capital th upon small th for hollow one. Right? This is the equation number 1 say. Now we assume that condition given is weight of hollow shaft is equal to weight of solid shaft. Right? This is given. So W weight is equal to m into g, mass into gravity, and mass is equal to rho into volume. So density is same, then rho, volume will be area into length, area into length is same, g equal to solid, weight of solid will be rho, area of solid section, length into g, rho, because both shaft are made of same material, so rho will be cancelled out, length is given same, g will be cancelled out. Finally, this will be equal to AH equal to AS. If you open it, then expression will be pi by 4 T H square minus T H square will be equal to pi by 4 T S square. Right? If you further simplify it, if you simplify this expression, then it will be, simplify this expression, then it will be here, this is dh square, make dh square common from this expression, pi by 4 will be cancelled out, and dh upon dh will be n square, right? And then this is t h square n square minus 1 equal to ds square, right? Now ds will be th under root n square minus 1, right? Put this value of ds into equation 1, right? Put this value of ds into torsional strength equation, right? Here in 1 we will put the value of ds here. Then what will happen? What will be the result? Then ds into equation 1, then torsional strength equation will become th cube upon dh cube, right, into n square minus 1 by 2. This is, then this will be n square minus 1 will be out from, and here will be the root n square minus 1. This is the value of ds, right? This is the value of ds, and here it remain, this is n to the power 4 minus 1. Clear? Now it can be open. This will be n square minus 1 and n square plus 1. So this will be, this term and this term will be cancelled out. Finally, what left? And here n is given already in the equation. So left terms are, this will be cancelled out. N square plus 1 upon n into under root n square minus 1. This is the comparison equation for strength of solid and hollow shaft in terms of diameter ratio, right? Now consider this value for n equal to 2, that means outer dia is the twice of inner dia of hollow portion, then th upon ts equal to 2 square plus 1 upon 2 into under root 2 square minus 1, and this will, when it will be simplified, we will find that th upon ts equal to 1.414 of Ts, or we can write Th equal to 1.414 of Ts. This will be 5 into 2.5 and this will be under root 3. That is comes around 1.44, right? 1.44 Ts. So what we see that T torsional strength of hollow for the given condition is 44% higher than the solid sapped, right? 44% higher than the solid sapped. It is also written in terms of, this whole equation can be written like this one. TH will be equal to TS plus 44% of TS, right? So this one is the higher amount by which, this one is the amount by which hollow section is higher. So for the given condition, we will choose hollow section in place of solid section, right? Hollow section in place of solid section. That is the final conclusion from this strength compression equations. Now we will compare the both sapped by weight, right? Compression and weight. Given condition are, in this condition, what are given? That length of hollow portion equal to length of solid portion is equal to L, right? There is same length, same material, same length, same material, right? And maximum shear stress is same in both condition. Clear? Maximum shear stress is same in both condition. And torsional strength is also same for both condition. T solid equal to T hollow. Only there is the difference between the weight of the shaft, right? There is the difference between the weight of the shaft. If torsional strength are same, if we write the equation here, then what will the value? TS is equal to pi by 16 tau max TS cube, and TH will be pi by 16 tau max, and here will be DH cube into n to the power 4 minus 1 upon n, right? This whole term is cancelled out. What we will have? TS equal to TH, right? And this will be n to the power 4 minus 1 upon n to be by 1 by 3. This is the equation number 1. Now, weight of the shafts differs. There is compression by weight. That means W hollow will be equal to rho A hollow into length into G, and W solid will be equal to rho A solid into L into G. If we compare it, then these both are cancelled. Oh, sorry. They are equal. This term and this one cancel out. This one cancel out. This one cancel out. What left? WH upon WS equal to area of hollow upon area of solid section. Right. Now simplify this equation further. exponential cross. This is the we are developing equation for this expression. It cannot be cancelled out, right? So what will we find? By putting the value of area, WH and WS will be pi by 4 cancel out, pi by 4 will be cancelled out, and in previous, when we are comparing the strength, we found that area of hollow section is equal to this one is the area of hollow section, and this is the area of solid section when they both are compared, right? So area of hollow section will be equal to, let's write it, pi by 4 dh square minus dh square upon pi by 4 ds square. They will be cancelled out, or finally it can be in form of, if we take dh square out of this expression, then what will be the equation? dh square n square minus 1, right? And this will be your ds square. Clear? This is equation 2. Now, from equation 1, put the value of ds into 2. From 1 and 2, what will be the new value for the weight compression equation? T h square n square minus 1 upon ds square, which will be equal to dh square n to the power 4 minus 1 upon n, and this will be equal to 2 by 3, right? So they are cancelled out, and finally expression will be n square minus 1 into n upon n to the power 4 minus 1, and this will be 2 by 3 for compression in weight ratio, right? Now put the value of n equal to 2. Why we are getting the value of n? Why we are putting the value of n equal to 2 into the equation? Because when the value of n is 1, then dh will be, outer dia will be equal to inner dia. Then this will be the condition that the given shaft is perfectly a hollow one, right? Perfectly a hollow one. There is because there is equality in both outer dia and inner dia. Clear? When we put the value of n equal to 2, so that says that n should be always greater than 1. It should not be less than 1, right? It can be 1.5 for 2. So we are considering the integer value of n, whole integer value of n, that is n equal to 2. Then the value will be wh upon ws equal to 2 square minus 1, right? And here it will be 2 upon 2 to the power 4 minus 1 and 2 by 3. If you simplify it, then value should be, it is when we simplify it, the value will come as 0.78, right? I have to calculate it. This value will become as 0.78. So finally it can be written as weight of hollow section is 0.78 times of solid section, right? So that means this expression is suggesting that weight of hollow section is less than the weight of solid section for given condition. It will be economical to use, it will be economical to replace solid shaft by this hollow shaft, right? By strength wise hollow shaft is economical, by weight wise hollow shaft is economical, so it is always preferred to use hollow shaft. From this expression, in the problems numerical problems, we calculate the value of saving in material, right? Saving in material, or it is also known as reduction in weight, and this term is equal to weight of solid shaft minus weight of hollow shaft upon weight of solid shaft into 100, right? In this case it will be equal to weight of solid shaft minus 0.7, or weight of hollow shaft is given 0.78 Ws upon weight of solid shaft into 100, so it is given 22%, right? That is the percentage reduction in weight. So percentage reduction in weight or saving in material, because shaft, if say shaft is made of alloy steel and we are making alloy steel, and per kg of alloy steel is quite costly, right? If there is the saving in material by the use of shaft of hollow section, right, it will be most economical to use hollow section over solid section. Clear? So this is the comparison of hollow shaft, solid shaft, and hollow shaft with solid shaft. Why we are comparing it? Because we try to use hollow shaft in place of solid shaft. It is always beneficial, because for the given condition, by strength, hollow shaft is having much strength in comparison to solid one, and there is also saving in material. Now we will cover another portion, that is when shaft in series and parallel connections, right? Shaft in series and parallel connection. So in this portion, first we will discuss what is compound shaft, right? When two shafts, let's read out, when two shafts of different diameter are connected together to form one shaft, right, it is then known as compound shaft. Clear? If we are talking about shaft in series and parallel connection, that there will be number of shafts, they will connected to each other, so they will form a compound shaft. Then what is the condition for compound shaft? Compound shafts are basically the two shafts of different diameter when they are connected for a purpose, right? Here I have made a diagram for the compound shaft. There is a shaft of diameter D1 and there is shaft of diameter D2. They are connected, right? This is the junction point for the shaft. A length of this shaft are given L1 and L2. This is your compound shaft. Now, when they are in series connection or parallel connection, it is very interesting in case of shaft, right? Now, we should not understand it like that. When these are the two shafts, say these are the two shafts and they are connected like this one, so we will say this is a series connection. As we have studied up to now, this is a series connection, and when they are parallel to each other, they will be known as parallel connection. This is wrong. This concept should not be made. It is quietly wrong, right? Because here their series and parallel connection was identified by the driving torque applied on the shaft, right? By the driving torque applied on the shaft. Read out. If the driving torque is applied at one end and the resisting torque, clear? If driving torque is applied at one end and the resisting torque at the other end, then the shafts are said to be connected in series. Clear? Here, these are the two shafts. Driving torque is here. This is our driving torque T, and this is T1, and this is the resisting torque at fixed end. This is T2. Clear? Condition, desirable condition, right? For this series connection is torque will be same for both the shaft. T1 equal to T equal to will be T, and total angle of twist will be equal to the algebraic summation of angle of twist for each individual shaft. This equation can be further rewritten as theta, and theta 1 will be equal to T1 into L1 upon I1P IP1 into C plus T2 into L2 upon IP2 into C2. If both shafts are made of same material, then what will be the expression? Right? If they both are of same material, then expression will be reduced to theta equal to T by C. Theta will be equal to T by C, and bracket will be L1 upon IP1 plus L2 upon IP2. Clear? That is the required expression for this case. When shaft in series connection, and what will be the value for shaft in parallel connection? When the driving torque is applied at the junction, this one is highlighting. When the driving torque is applied at the junction of the two shafts, and the resisting torques are T1 and T2 at the other ends of the shaft, so then shafts are said to be connected in parallel. Here is the junction point of these two shafts 1 and 2. When driving torque is applied at this point, right, at this point, clear, then the resisting torque will be developed at both ends. Here it is T2 on shaft 2 and T1 at this one. In this case, because driving torque is applied at the junction point, then angle of twist will be uniform throughout the shaft, right? Theta 1 equal to theta 2 equal to theta 1 equal to theta 2 equal to theta, right? Theta will be constant, angle of twist will be constant, but turning moment developed will be equal to the algebraic summation of turning moment in each shaft, right? We can explore the expression. T will be equal to T1 here will be equal to C theta 1, right, into IP, because T is equal to T upon IP equal to C theta by L, right, and C theta 1 IP upon L, right, L1 plus C, this is C1, C2 theta 2 into IP1 IP2, clear, upon L2. C, if shaft material is same, then C will be constant, theta is already constant, then this expression can be expressed as C theta in bracket will be IP1 upon L1 plus IP2 upon L2. Clear? Right? So this is all about the shaft in parallel and series connections. For the lecture we will discuss the combined bending and torsion on the shaft.